In the previous tutorial, we introduced Fourier transforms and Fourier series, and we showed how Fourier transforms can be used to solve PDEs in a similar way to the Laplace transforms, while Fourier series tell us what frequency components make up a given function. Let's now unify these two ideas. If we compare the Fourier transform formula to the complex Fourier series formula, we should notice they seem to be saying pretty much the same thing. The only difference is that the Fourier transform is an integral over a continuous spectrum of frequencies, while Fourier series sum over discrete frequency steps. This gives us a fresh perspective on what the Fourier transform means. It gives us a continuous function f hat of a frequency k that describes the spectral density of our function f at the frequency k. For example, if a musician plays a guitar chord at, say, 3 different frequencies, and we record the sound wave produced in the air and take its Fourier transform, we can expect to see significant peaks in our function f of k at frequency values k corresponding to the 3 individual notes in the chord. We will also find smaller peaks at double, triple, and so on of these frequencies, since these are the higher harmonics of the fundamental frequencies. The purer the frequencies of the notes, the cleaner the peaks will be in the Fourier transform, and in the limit of a pure sinusoid, the frequency spectrum will contain perfect Dirac delta functions, which are point spikes at the precise frequency. The squared magnitude of the Fourier transform, which is what we're really plotting here to visualize it easier, is called the power spectral density of our function f of t, representing the intensity of each frequency making up the function. And there are 2 important theorems that we should hopefully find quite intuitive now that we know the meaning of the Fourier transform. First, Parseval's theorem states that the total energy of a time domain signal, which is the integral of its squared magnitude, is equal to its integrated power spectrum over all frequencies, which is a statement that the energy is conserved whether in the time domain or in the frequency domain. Second, the wiener-khinchin theorem states that the power spectrum of a function f is equal to the Fourier transform of the autocorrelation of f, where autocorrelation is like a convolution with itself with a sign change. The autocorrelation therefore measures how similar f is with itself when translated by the parameter tau, and then integrates over all delays tau. As shown in this animation depicting the autocorrelation of a rectangle function, the autocorrelation is highest when there is maximal overlap between the function and its horizontally translated version, and here that overlap is maximized for no translation at all, or t equals 0. The Fourier transform of that function gives the power spectrum of f directly. Lastly, we can now use Fourier transforms to explain why we classify linear second-order PDEs as elliptic, parabolic, or hyperbolic. Let's consider a linear second-order PDE with constant coefficients a through f, and we take the Fourier transform of both sides of this PDE with respect to both x and y. Since the Fourier transform of a derivative of a function is given by I times k times the Fourier transform of the function, we can evaluate the transformed left-hand side as follows. We can disregard the case where u hat is 0, since this would correspond to a trivial solution with u equals 0 everywhere, so we can instead set the expression in the first term to 0. Notice that this equation precisely matches the form of a conic section in the variables ikx and iky. The conic section curve that we get is called a nodal line, and it may be an ellipse, parabola, or hyperbola, hence the naming system in direct analogy with the conic sections. For a multivariable Fourier transform, such as the one we have taken here, the transformed coordinate space is a multivariable frequency called k-space, where kx is the frequency of waves in the x direction and ky is the frequency of waves in the y direction. As you can hopefully tell, Fourier transforms are an incredibly powerful tool in analyzing things with wave-like behavior, and their applications stretch far beyond our desire to use them to solve partial differential equations. In general, this field is called signal processing, and its real-world applications are incredibly broad. They include exploring how MRI scans and CAT scans work in medical physics, how optical coherence tomography works in ophthalmology, biology, how infrared and NMR spectroscopy works in chemistry, how X-ray diffractometry works in crystallography and materials science, how modulation of radio waves works in telecommunications, how speech recognition and audio filters work, and so much more. I encourage you to look into these topics in your own time if you're interested, but for now we're just here for the use of Fourier transforms in solving PDEs, so let's check comprehension before putting them to good use in exactly that with the wave equation.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.